Hello everyone, hello students for GCSE and IGCSE programs and all other students interested in math. Right now we are on sets, we are going to consider what sets are, how it works, how to visualize sets using Venn diagrams or just simple listings. So that's why I consider it's a very significant topic for you guys and for your comprehension is better to go through revision as well. Just if you're new here, if you're just first time visiting my channel, please subscribe. That's how you can support me. And also share this video with anyone, like with your mates, with classmates, and with your friends. That's gonna be good. Alright, and we're gonna go through explanations for sets. So we'll first start from definition. Here I just provide several slides for that so that you can copy, print screen, and use as your footnotes in order to refresh your maybe drawbacks, maybe something that you didn't get at your classes. That's going to be a cool idea if you just save that, or just every time you can move back to this video and just go over again. So grab your pens, grab your notes, and let's get started. Okay, so we're gonna start from definition. So we can say that set is just a collection of objects or any other things. So in reality, you can assume set as the container, okay? So this is just a box that contains other stuff that you like. You put different elements inside. So in mathematics, most of the case, you'll have to deal with numbers. So that's why in this case, elements are represented by numbers. But in general case, like wider applications, simply container that can contain any different objects of things. So it might be basically pupils, students in class, or students with a specified criterion. So you just select several students from the class and just put in container, and that's how you can mark up as the set. Okay, so also if you're just investigate some phenomenon and you measure some physical quantity, let's say temperature or pressure, and you have specific or limited precision for that and accuracy. So you measure this quantity and you just writing up values, and that's how you can also create the set of elements. For example, for a day, for the average temperature for first calculations. All right. So this is, as you can see, more like wider application. Okay, so and we use this symbol in order to say that the element adhere or is from the set. For example, let's consider a set of positive integers z plus. So that's how we denote positive integers. In this case, we can say that 7 is from the set. Okay, if you mark this as set A, you just put the letters. So 7 is going to be from set A. Okay, so what about number? So that reads the number of elements in set A. So that means if we put n, z, for example, z plus, as you understand, there's going to be infinite many elements, because the set is not limited from the right side, because if you represent this set on the number line, for example, starting from 0, but not including 0 because it's z plus, so positive integers. So in that case, your set will have no any upper boundary. So it's unlimited from the right side. And you can find many numbers. So that set is unlimited. Okay, so I hope you get this idea. But for example, if you have positive integers which are less or equal than 20, so you started from 1, 2, 3, and so on up to 20. That's how you can set up your set z plus. Okay, so that's how you can set up z plus, and you will use curly brackets. In this case, if you just count the elements, it's going to be a specific number which is limited, and in this case it's going to be 20 elements containing z plus, which satisfy criterion less than 20. Okay, less or equal than 20. And now it's logically to say that we can put different combinations from your main set. In this case, we can consider, for example, set A, which contains elements 2, 5, and 8, 2, 5, and 8, and consider set B, which also contains elements 2, 5, and 8, and on top of that, it has extra elements like 3, 9. So in this case, obviously, we understand that A is a subset of B, because subset of B, if we denote like sort of like area, specific area, so we understand that set B contains set A inside, all right? So there are elements 2, 5, and 8, and on top of that, somewhere like in within set B, but not within set A, we can also find elements like 3 and 9, okay? So in this case, A is a subset of B, and we can define a subset A of B in case if all elements of A are also elements of B. So those elements are common for set A and B, but on top of that, set B is a bit wider. So in this case, set A definitely is less in quantity than set B. So that's why A, what is called subset of B. However, if we add into set A those numbers 3 and 9, we'll get two sets A and B to be equal. So in this case, we can define two sets A and B are equal if their elements exactly the same. So in other words, if set A we set up as 2, 3, 5, 8, and 9, it will contain all elements as in the set B. So in this case, we make both sets are equal. Okay. What about proper and improper subsets? So set A is called proper subset of B if every element of A is also an element of B, but A is not equal to B. So in this case, we can say that A is a proper subset of B because elements 2, 5, and 8 can be found in set B. However, they're not equal, so that means set B is a bit wider. It contains a bit more elements, okay? And we denote like, remember this sign that means some element X from the set, so it adheres to the set A, for example, but in terms of sets, we use just like C, okay? Letter C. That means adherence, okay? So I hope you get it. And now we move in next in order to how we can define universal set. What does it mean universe? So universe is something like big, okay? So that means that universal set should contain all possible elements within the given like conditions or within the given statement of your problem. So in other words, we can define the universal set as the set of all elements under consideration. So sometimes it's called a sample space, and most of the case you heard this word from statistics, okay? Because statistics has deal with sets, with elements. That means if we consider positive integers, z plus, which is less or equal than 100, elements from 1 up to 100 will represent universal sets. We use this dots in order to indicate that this pattern is like keeps going, okay? It means that we have the pattern every time we add 1 because we just list in all positive integers starting from 1 and goes up to 100. So that's why we make a little skip by denoting those like dots, all right? So that's universal set, okay? So the universal set can be specified within given conditions. In a case you have, for example, cards and you consider probability, so playing cards and probability, so your universal set will represent those cards, okay? If you consider taking one card out of the game, it's going to be a specific like subset or proper subset representing just one card taken out. But possibilities for this card might be just one out of everything, right? Out of your universe. Okay, so be careful about universal set, and in statistics and in probability theory, you need to be able to define universal set or sample space. Otherwise, it won't be possible for you guys to calculate probability. All right, so empty set, interesting term. So empty set. The set might have no elements. Why is it done? So probably I think it's done for programming computer language, where you need to define some like set containing no elements, like empty sets, because programming having deal with arrays, okay, and arrays basically are sets. It might be multi-dimensional arrays. In this case, it's easier to manipulate as if you're just manipulating math with sets. Okay, so that's why there is some necessity in order to use empty set. Okay, so and make sure you understand that empty set is always a proper subset of any other set. So it means that no matter which set you consider, the empty set does exist and it always exists. Okay, so that's why it's going to be a proper subset of any other set. Okay, except for maybe, so if you consider empty set, so empty set as well is not going to be a proper subset. But most of the case you're considering non-empty sets, so that's why this empty set will always be a proper subset. Okay, so hope you understand. Okay, so we achieved an interim goal, and right now we just have a look at the complement of the set. So what does mean complement? I'll show you in this way. First of all, graphically it's much easier to perceive. So let's assume you have some set, okay? Let's be the area where you have, let's say, universe, the set within given conditions, okay, of the problem. And let's assume you have set A, no matter like what it means in given conditions. So let's say this is the area for set A. Okay, so here is the rest part, which we denote as A prime, so we use apostrophe, and graphically you understand that universe contains of set A and the rest part, which is called not A or A prime. So in this case we believe that A, which is another set that complement your set to universe. So in other words, the complement of A is the set of all elements of the universe which are not elements of A. And indeed, if you take any element, random element from A prime, so let's say X prime, is not going to be the element of set A. So they sort of separated. So those sets A and not A are isolated, they're separated, and they're separate sets. However, together they arrange universe. So that's why for every set that's going to be a complement that's basically in addition to your set arrange the universe. So in this case, if we consider U as Z plus, so positive integers, and A as prime numbers, so the set of B is going to be A prime because it's going to be the complement if we define set B as the set of elements which are not primes. Okay, so primes and not primes. Also, we can define, like, for example, odd numbers and even numbers. In this case, if we consider and they're positive, right, both are positive, as normally we assume. So for Z plus, they'll also be considered as A and not A. So basically A and the complement of A. So I hope you understand. We use this notation, so be careful. It's not sign for differentiation, because normally we also use this prime for differentiation, and that's going to be the first derivative, which is df dx. But in this case, it's just notation, so that's why it's not differentiation. So be careful about that. Don't try to mess up. I hope I clarify this. It's just simply notation. And notation is very crucial within context. Okay? And we go to the list of those symbols that we use today. So it's going to be a notation for sets. So first of all, we use curly brackets. They basically means that we define sets. So set A is defined through curly brackets and elements inside. So universal set is just, it defines all elements under consideration. So in other words, it's sample space from statistics, and from A, number of elements. So here, this is adherence of elements of the set. So X from A. This is not, so if we actually, I forgot to mention, if we cross it out, that means X is not from A. So X is separate element and it's not from A. So this is empty set. Okay. And we have also subset and proper subset. So this subset you can consider as set from or equal set. That's why you have notation like this notation for GCSE and mostly for universal maths. And this is just the node proper subset, so there is no equalities, that's why you just need to use C, but not like subscribe in this case, okay? A set contains proper subset is a subset which contains part of elements of your set, okay? And we have the last one, what is called intersection and union. So in order to show that, we need to go to Venn diagrams. We're going to use what intersection means and what union means. So intersection and union have very significant symbols for Venn diagrams, and Venn diagrams is just a tool in order to represent sets in a proper way. Alright, so now we are going to consider Venn diagrams.